When we talk about waves, it's important to differentiate between a wave itself and the thing that a wave passes through, which we call the medium. Let's imagine a simple pulse travelling down the rope. This pulse is a wave that's created at the end of the rope, which we call the source, by something that disturbs the rope in some way from its original rest position. This disturbance at the source has a knock-on effect, disturbing the bit of rope next to it, which in turn disturbs the bit of rope next to it, and so on. This pulse therefore travels down the rope, transferring energy from one side to the other. The problem is in defining what exactly is moving along the rope, from the source to the other side. Clearly no rope particles are moving along with the wave. Instead, each rope particle is just being briefly disturbed by the pulse as it passes through, but then it returns to normal afterwards. We call the travelling disturbance the wave, and the thing that is being disturbed the medium. We now switch from a pulse to a repeating disturbance, like shaking one end of the rope up and down continuously. And we see each disturbance starts at the source and travels down the rope, and we have a periodic wave. First, we will just look at the movement of one particle on the rope as the wave passes through. We see that its motion is simple, just bobbing up and then down, going past its rest position. We call the difference between the particle's position and its rest position at any given time its displacement. If we plot a graph with time increasing along the x-axis and the displacement of the particle on the y-axis, we see that it sketches out as something like this. The time it takes for the particle to undergo one whole cycle, going one way, then the other, then back to the start, is called the time period of the wave. Now let's look at the whole rope again, but this time freeze time and just look at its shape. We notice that the pattern of the rope appears to repeat itself. Look at all these points highlighted and notice that they all have identical displacements. We say that these points are in phase, since they all have the same displacement, and because when we unfreeze time, they will all undergo the same motion as each other, in this case back downwards. The shortest distance between two particles that are in phase is called the wavelength of the wave. We can see that if we go to any particle and specify its displacement and its motion, it will be identical to that of a particle that is one wavelength ahead of it, and two wavelengths ahead of it, and three wavelengths behind it, and so on. The wave repeats itself every wavelength. With definitions of the time period and the wavelength, we can define a couple other terms that describe waves. We said the time period is how long it takes a particle to undergo the full motion cycle caused by the wave. The frequency is the inverse of this. It is how many full cycles a particle completes per second. You may have noticed that given these definitions, the frequency must be equal to 1 over the time period. Something slightly less intuitive is that the speed that this wave travels at, v, is equal to the wavelength of the wave multiplied by the frequency of the wave. The amplitude of a wave is defined to be the maximum displacement that a particle reaches during its motion cycle, the furthest away distance from the rest position. A wave on a rope is an example of what we call a transverse wave. It is transverse because any given particle in the medium does not move in the same direction as the wave, but instead perpendicular to it. When the wave goes along the rope, it does so by moving the rope particles up and down. A longitudinal wave works differently. Instead of moving particles perpendicular to the wave direction, up and down, it moves them parallel to the wave direction, right and left. We completed the discussion above using transverse waves like waves on a rope, but it can easily be mirrored using longitudinal waves, such as sound waves, which could also travel along a rope. The discussion is exactly the same, talking about the displacement of each particle from its rest position. The only difference now is that the direction that the particle gets displaced in is no longer perpendicular to the wave direction, but parallel. Transverse and longitudinal waves are both used to transfer energy and information from one place to another, without actually moving anything physical along with it.